All right, so we're going to discuss how to find the limit graphically. All right, so we're going to do a few where we have to graph, and then we'll do some where the graph is already provided. So my graph is just 4. This is just y equals 4. So I know that I have a horizontal line at 4. Well, it'd be helpful if I could draw a nice line. Okay, so a horizontal line at 4. Okay, and this is saying what is the limit as x approaches negative 4? Well, what we have figured out is if this is a number here, just a integer, and there is no, not even just an integer, just a number, and there's no variable here, then that's going to be the limit. Because as I approach negative 4, my y values are consistently at 4. So I'm assuming that when I get here, I will reach that right there. So the limit as x approaches negative 4 of 4 is equal to 4. All right. On number 2, we have a piecewise function. So I'm going to graph this one first. So this is y is equal to negative 1 when x is 2. So when x is 2, my y value is negative 1. So I have a point right here. And then this is the graph of a parabola. So you could do this by hand if you wanted to, or you can choose to graph it in the calculator, and then you can put a hole when x is 2 because it can't equal that graph when x is 2. All right. So let's grab our graph, and we're going to graph the negative x squared plus 4x minus 4. Get a picture of that. All right, that looks like this. Now, I would kind of like for my table to fill in on its own, so I'm going to go to second window to that table set menu and change my independent variable to auto. That way, when I do go to my graph, I have a table that's filled in. So obviously, right here at 2, 0, that's going to be my vertex. And then I just need a couple of points on either side. So I'm just going to go with the 1, negative 1, and the 0, negative 4. All right, so 1, negative 1, 0, negative 4, and then I have my vertex here. And remember, wherever that vertex is, that makes your line of symmetry. So if I have a dot that's 1 to the left, I also have a dot 1 to the right, and same thing with my other point. So I would just draw that in. All right, so it told me up here, though, that y is equal to this when x is not 2. So when x is 2, I'm going to have to put a hole in my graph. So I go to where x is 2, where my graph is at, and I'm going to put a hole right there. So if I'm looking at this graphically, they want to know the limit as x approaches 2. So as I get closer and closer to 2, what are my y values getting closer and closer to? So let's say that I had chosen the point 1, that I'm at negative 1. 1.5, I'm here. I'm getting closer and closer and closer to this location right here on either side, and that's a y value of 0. So the limit as x approaches 2 of f of x is equal to 0. As my x's get closer to 2, what are my y values getting closer to? All right. So we have another piecewise function. I'm going to go ahead and plot this point right here so I know that y is 1 when x is negative 3. So when x is negative 3, my y value is 1. And then I know that y is equal to this equation, this parabola, everywhere except when x is negative 3. So I will have a hole in my graph at that point. So we're going to go ahead and graph that equation. So I have a negative x squared minus 4x minus 1. And I see that my vertex is at the point negative 2, 3, so I like that point. I'm going to choose that. I also see that I have a point here at negative 1, 2, and a point at 0, negative 1. So I'm going to go ahead and plot those points. So my vertex, which is at 2, 3, then I have a point at negative 1, 2, and another point at 0, negative 1. And then I'm going to mirror those to the other side of this axis of symmetry. So I have a point here and a point here. And I will draw those in. But I do have a hole in my graph when x is negative 3. So I'm going to go to negative 3, go up to that graph that I just made, and put a hole there. All right, so when my x value is approaching negative 3, so as I get closer and closer to negative 3, my y values, as I travel along here, getting closer and closer to this spot, and same thing on this side to this spot, which has a y value of 2. So the limit as x approaches negative 3 of my function f of x is equal to 2. All right, so we have some graphs that are already drawn for us, and we're going to come up with the limits on these. So this would be the graph of this right here. And we want to know the limit as x approaches 3. So as I get closer and closer to an x value of 3, they want to know what the y value is. So if I look right here, I'm getting closer and closer to an x value of 3, and it looks like I'm approaching a y value of 4. So closer and closer to an x value of 3, still approaching this spot, which is a y value of 4. So the limit as x approaches 3 of x minus 3 over the square root of x plus 1 minus 2 is equal to 4. All right, the limit as x approaches 1. So 1 is right here, an x value of 1. So as I travel along, I'm getting closer and closer to this location right here, and on this side, same thing, this location right here. That is a y value of, I'm going to say, a negative 1/4. Okay? If you get really, really close, I'm not going to dock you for that, because it's kind of hard to tell since we're just going off of a graph. I will tell you, though, that if this circle is connecting with the top, it's probably a 1/4. If it's a little bit down, it's a 1/3. If it's in the middle, it's a 1/2. So I'm going to say the limit as x approaches 1 of negative x minus 1 over x squared plus 2x minus 3 is equal to a negative 1/4. All right, so the limit as x approaches negative 2. So I look from both sides. So this graph, as I get closer and closer to negative 2, is going to continue going up and up and up and up and up to positive infinity. And same thing over here. It's just going to keep going down, 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 down to negative infinity. So therefore, since I am increasing and decreasing without bound on both sides, that would be a limit that does not exist. Okay, and we talked about that in part 1 of this video series. So this is a limit that does not exist because of the increasing and decreasing without bound on both sides. If I had said that I was approaching negative 2 from the left, you would say positive infinity, or from the right, negative infinity. But they are both approaching two different things anyways, so that will not work for us. So the limit as we approach negative 3, again, same as the last question, we are approaching from the left and going towards negative infinity, and from the right going towards positive infinity. So therefore, this is also a limit that does not exist. So the limit as x approaches negative 3 of the function x plus 1 over x squared plus 4x plus 3 does not exist. All right, so this time we are approaching 3, which is right here. So we won't be focused in on this side. We are focused in right here. So as my graph moves along towards -3, I'm approaching this y value right here. Same thing on this side, approaching this y value right here, which looks to be about a -1/2. So the limit as x approaches 3 of the function x minus 3 over x squared minus 8x plus 15 is equal to a -1/2. All right, so as we approach 1, so this location right here, as my x values get closer and closer to 1, my y values are approaching this right here, which is 1/4, and that is happening on both sides. So the limit as x approaches 1 of the function negative x minus 1 over x squared minus 6x plus 5 is equal to 1/4. All right, and now let's talk about a tangent. So we're approaching a -π/2. That is this location right here. If you look on this side, we are approaching -infinity. This side, +infinity. So this would be a limit that does not exist. I do prefer that you put this in the front of that. All right, and let's talk about, we have a couple more. So this time we are approaching one from the left. See this minus sign from the left. So if I'm looking at 1 from the left, looks like I am approaching this location right here, which has a y value of -1/4. So the limit would be -1/4. Again, I would prefer you put all of this in front of your answer. And for the last one, still approaching from the left, we're approaching -4 from the left, and it looks as though I'm approaching this spot right here, which is a y value of -1. So the limit as x approaches -4 from the left would be equal to -1. So let's talk about some properties of limits and direct substitution. So some basic limits when you're using direct substitution are as follows. We're going to let b and c be real numbers and n be a positive integer. So if I am taking the limit of a number, just a real number, as x approaches c, my limit is just going to be what that number is. That's just like the one where we graphed the 4 that was just a flat line. If I'm taking the limit of any number, so x represents any number, this is a specific number, as x approaches c, then all I'm doing is plugging that c directly in for that, and that's my limit. All right, same thing here. I would just be plugging the c in right here, and I would get c to the 7th. So whatever I was approaching, I would just raise that to this power. All right, and then the limit as x approaches c of some nth root, that's a positive integer, of any number, I'm literally just going to take that number and plug it in, and that would be my limit. C has to be greater than 0, though, so that we can avoid those imaginary numbers. All right, so some properties of limits. We're going to let b and c be real numbers, n will be a positive integer, and f and g are just functions. So if I take the limit of x as it approaches c of this function, I get L. Same thing with this, I get K. So if I were to take and just multiply my my limit here by a number, that's the same thing as taking the limit of my function and just multiplying it by a number. Sum or difference, you can take the limit of one function, the limit of another function, and just add those together. All right, multiplying, I can take the limit of one function times the limit of the other function. Quotient, same thing. You can take the limit of one function divided by the limit of the other function. Just make sure that the bottom limit does not equal 0. And for the power, I would just take whatever the limit is of my function and raise that to the power. So those are just some properties. So what we're going to do is we're going to kind of practice these properties, practice using these properties. So on the first one, I am just taking the limit of something that's being squared. So I can take that 4 and directly plug it into that. So if I take 4 and square it, that gives me 16. So my limit is 16. So I just used direct substitution. I took the number I was approaching and plugged it in. You can do that a lot, and it's probably my favorite way to solve for a limit if it's possible. All right, so I see here that I have 5 times my function. So all I have to do is take 5 times the limit of x as x approaches the 4. All right, so in other words, all I'm doing is plug in here. So the limit of x as x approaches 4 would be 5 times 4, which is 20. That would just be multiplying by a scalar multiple. All right, here we have quotient. So we're going to use the quotient rule. So the quotient rule says that you can take the limit of the top and divide it by the limit of the bottom. So if I took the limit as x approaches pi of tangent x, and I divide that by the limit as x approaches pi of x, then this is what I get. All I have to do is take that pi and plug it in right here. So the tangent of pi, if you think about your unit circle, pi is right here, and that pi has a point of -1, 0. So if I took the tangent of that, that would be 0 divided by -1. So tangent of 0 would give me 0. And then if I plug the pi in here, remember if you just have one thing, you can plug into that. So I get 0 divided by pi, which is just 0. And that is my quotient rule. Okay, so here, I don't have any rules that have to do with square roots, so I'm just going to directly substitute in. So I get the square root of 9, which is 3. So my limit would be 3, and that's another just direct substitution. All right, here I am multiplying x and cosine x, so that would be a product. So this is going to be our product property. I can just take the limit of x and the limit of the cosine. So if I take the limit as x approaches pi of x, and I can multiply that times the limit as x approaches pi of cosine x. All right, so I plug the pi in here, and that just gives me pi. I plug pi in here, and I have to take the cosine of pi. Remember, cosine of pi would be your x value, so pi times -1, so I get negative pi as my limit. All right, and for this last one, we have a sum inside and then being squared. So all you have to do is take the limit of the first one plus the limit of the second one and then square your resulted answer. So if I take the limit as x approaches 3 of x, I will add that to the limit as x approaches 3 of 4, and then I will square that. So if I plug in here, remember the limit of x, all you do is plug in. So I get 3. If I take the limit of just a number, I get just that number, and then I'll square this. So 4 plus 3 is 7, squared is 49. So the limit would be 49. So let's practice some direct substitution. So you can directly substitute to find the limit on any problem until it gives you a problem area, like a 0 in a denominator. So I'm going to go ahead and plug in this -1 here. So I get -1 squared plus -1 minus 6. All right, so the limit as x approaches -1 of this function would just be -6. Because -1 squared is 1, minus 1 is 0, minus 6 is -6. I can do the same thing here. I can plug this -1 in, and I see that because -1 plus 3 is not going to give me a 0 in this denominator. So I have -1 squared, and if you're paying attention, you know that we just did this on the previous problem right here. So I already know that the top is going to be -6. Plug that -3 on the bottom, so we get -6 over 2, and we get -3 as our limit. All right, I did make a side note here that if x is approaching -3, we would have to evaluate using a different method because the function is undefined when x is -3, because that would give me a 0 in the denominator. So really, you can use a lot of different ways to figure out what your limit is. You can graph it. You can do direct substitution. And sometimes it's easier to do one or the other. Okay, if you have a lot of holes in your graph, graphing it on a calculator might throw you off just a little bit because you can't see the holes. But the holes really don't have any bearing on what your limit is. Okay, so try direct substitution, first if you're getting to choose the way you do it. And if that doesn't work, then you can maybe graph it and try that way. We will learn more ways to find a limit in the next lesson, but for now, direct substitution and graphing.